This conference will now be recorded.
Hi, John.
Hi.
Okay.
Okay, good. So the challenge here has been, I've been in test and measurement for a while, and I've been in broadcasting for a lot longer than that. And one of the things, for all intents and purposes, all the things we've been going through, we've used test equipment to measure, determine the errors, and how we can actually measure level of signal to noise and how much bits and all like that. But one of the challenges we have today is actually how do we actually represent or score how people see video. It's one of the things we really haven't done, because we can give you a really bad score on a piece of video, and most people today will watch it. You know, they say, oh, because it's the content that matters. Now, if you kind of look at this is kind of a blown out version of perception. The idea here is that in our own human brain and everything, we do a lot of compression, get it down to a very small amount of bits that actually this conscious perception. So it's a very small amount of information. So in this result, so people view things differently than if I can build a piece of test equipment for it. And so we're trying to kind of give you an idea of that, because here is, wish I had better eyesight, I could see the screen there. Anyway, so basically eye movement. So the eye is always darting around, filling in the information. So you have really heavy concentrated data, you can miss things. So you have that. You also have the sensitivity of the register and the so we're going to look at the contrast and the colors. And the other one is actually the experience of the person looking at the video. Because I can look at something and say, oh, that looks bad. My wife's saying, what are you talking about? So it's a different of how we view things. So it's our how we look at things. So if you take a look at this is a still photo, but if you look at it long enough, you see everything starting to move, because your eye is darting around trying to see the detail in this. So it gives you that illusion. So this is sort of that there's too much data here for you actually to take it in. Now this is a slide I made a while back, and this is a very common, a lot of people look at this optical illusion and done it for it, but I put a waveform next to it, and I'm measuring right. Is there a light on this thing?
Yeah.
Top. So if you look right down over here, that's the line I'm looking at. If I go to the next, now I'm looking at that line. If you notice, the scope didn't change levels at all. But everyone in this room believes the top part is darker than the bottom part until I hide the curve. Your brain does that. So on my waveform, I can measure it and say one thing, but how people perceive the video is entirely different. So if we are setting up and creating video for waveforms, then we're in pretty good shape. But we don't. We have to start realizing that what we're doing is creating stuff for people. Go back. Isn't that crazy? Everybody in this room sees it differently, but the waveform doesn't. And it has to do with that curve. You think your brain thinks there's a shadow underneath there. Kind of cool. Anyway, so the idea of this particular slide is to show you that the human perception and how we can measure things with a piece of test equipment aren't necessarily the same. And so in the old days, signal to noise was the big thing. When I started in the business, signal noise and roll off. Those are the two things we always look for, right? And that we measured that like crazy. And now we're getting into digitizing stuff. We're looking at blurring, and we're looking at the blockiness. So how do we measure these things? And the other thing is, some of the ways we measure these things, we can only see what the last layer did to the video. We don't see what the original looks like or can compare that original video. So one of the things we in the world try to do to figure this out, this is sort of a method that actually we used at Crawford when we were trying to pick out a standard def to HD convert to HD. So we got all the editors and all the engineers in a room, and we showed, all right, here's our reel. This is what it looks like. And then we'd put it through the different encoders that people brought to us, and we'd score them. Which one looks better, which one looks worse. And it was the opinion of the group. In this particular case, you'd actually go out and hire a group of people to come into a room like this. First thing you do is you teach them what good video looks like. Then you run a bad piece of video through there. Then you start looking at your test stuff, and you ask them to score this. And this is called the mean opinion score, MOS. So, MOS score. So this is something we used to do when we were making encoders and like that. Well, Tektronix a while back, actually, so you'd actually take all the averages here and you come up with this score. So this is what the average people look at. And some people in the audience are going to have more experience and understand video better than the others. And actually, and if you go to let them go to lunch and come back, those guys are going to tell the ones that didn't know anything what they're supposed to be looking for, and now you get a whole different results after lunch. So those are the challenges about this. So Tektronix had tried to create something similar to this in our PQA, Picture Quality Analyzer. This required two things. You needed a reference signal, you needed the original signal, original video, and then you put that video through the encoder, and then you do a comparison of the two. And this had to be frame accurate, and we go by pixel to figure out what is different. And if you look here, so that's the original, and there's the test. And if you look at the test video around the trees, you see there's less detail. In the bitmap, you see there's a lot of white in there. Right in there like that. So that is showing you the difference, where the difference areas are. And so that's showing you the softening up of the video. We're losing that detail in those trees. So this actually has turned out to be, we've been able to tune this to actually do a very good job of recreating how people view video. Because we also added a whole bunch of other things, because the other things how people view video is they see things coming towards them as more of an interest. So you can set it up so points of interest, or things coming toward you have more points than things out on the outer edges. So you can apply that to it, and you get close to a correlation of how people see video. It gets pretty close to that. The challenge is I have to have the original and compare the others. You can't do this with live video. This is something what we've been trying to pull off. How do you do that? And you can kind of see on the pit chart here, I take the reference and the master, I compare the two, and I come out with what has changed. And the nice thing about this is it's repeatable. So the encoder, you tell the encoder guy, well, yours wasn't as good as the other guy. So wait a minute, I just fixed it. I got a little bit better now. Let me go change it. Well, I don't have to get 500 people back in the room to do my test again. I can run it through this. So it gave it a easy way of actually seeing. And in labs, you're working on kind of your encodes. Did we make it better? Did we make it worse? Those are the kind of things that let you do it. So now, moving into how do we evaluate this in the real world? Because this is in a test environment. When we're talking about a non-reference or a single-ended system, we have to take a look at the video and determine with that scene what's wrong with it. Now, we can take a look at some of the elements of, is the stream good? Do we have some drop bits? Do we have some energy on the blocks showing blockiness and things like that? So we can do those kind of things. We don't have to worry about lining the picture up. But the challenge here is it doesn't correlate well with how people view video, because we're looking at the technical parts of the video, not the essence itself, how it looks. Because the problem is some of those things we can score poorly, but that's actually part of the video. That's actually snow. That's not noise. So these things, how do we actually make it better? So when we take a look at this, and this is sort of comes from our Century product line, we have several layers of QCs available to us. So we have quality of service. This is just looking at the pipe. Did it deliver to me the same stuff I put in on the other end? Did the bit rate? Am I getting drop packets? Am I losing stuff? So it's just telling me that the quality between point A and point B is good. Doesn't tell me if it was bad video coming in. It just tells me I didn't lose it there. Then we can decode it a little bit. And now we can take a look at some things where we call this DVQ. And so we're going to look at more of the spatial features. We're going to look at try to look at some of the parts of the video that we can decode and see on that first layer. Not fully decode, but I can look at the DCT coefficients and see if those look correct, and so I can get an idea of how it looks. Then you can go even farther, and this is where you actually decode it all. Now I have two paths on this thing. One of them I'm looking at is which typically we do now, is quality of experience. Quality experience is I'm actually going to look at that energy on those blocks and see if it's how blocky is it. Try to measure those elements to predict how people will react to it. But we never got we really got that corresponding with how people see it. We still have a lot of false positives and miss some stuff with it. So then we came up with this TechMOS. What we're going to do with TechMOS is we're going to get the same accuracy as we do with a dual stream system, but without that. And we're going to use artificial intelligence to pull that off. We're going to be able to look at it. And the other thing about this is I'm looking at the quality of the image. And that will pick up even the stuff that was recorded on a encoding beforehand. That is now part of the video. Now, I can even look at that and say, this just looks bad. Because I'm looking through, I'm just saying, is this good video or not? And that's where the problem is with the quality of service. I have to look at the encode part of it. If there's encoding errors that have been carried through that are now part of the video because of the last encode, I can't point my finger at those. So being able to look at this, without this reference, I want to be able to do single-ended. I want to be able to, there's a couple of modes I'm going to do. First, I'm going to teach, just like I taught the people in that room, I'm going to teach AI what good video is and what bad video looks like. The only difference with AI is I have to teach it in sections. I have to say, this is blurry, this is no blur, this is blurry, this is really blurry. And so I give it those samples. I tell it this is MPEG-2 errors, good, bad. And so MPEG-4, so I'm going to teach it all of these different errors. And if we come up with some new way to story video, we can teach it that too. But right now, so what we're going to do is we're going to train the video. We're going to train the AI or these engines that we created, and we're going to send it video that's been scored by real people who've said, and also with our PQ, we're going to use that technology to score how video looks. Well, is this good? Is this bad? Or is this unwatchable? And I'm going to be able to score it. Once I train it what it's like, then instead of having a reference exactly the same, I'm comparing all the frames to each individual images, comparing it to other stuff, looking for those signatures of that noise. Whether it's blur, MPEG-2, MPEG-4, or noise, I can actually teach it that. The only thing video that kind of is challenging for us is animation. So we had to have a special animation mode in order to do that, because animation is just always looks bad if you don't think of it as real video. So we had to kind of tell it, we had to kind of flag that. So when you take a look at it, you can see where we decode the signal. And one of the things we do right now is we take the black and white, we take the wide channel and look at it there, because you can see noise and you can see the black, you can see this information in there. There's more resolution in that area, and we want to be able to pull that out. And so we're going to come up with a similar score, and it's going to score it just like we did that NMOS, that MOS score. So we're going to come up with that mean opinion score and give that same score 5 through 0, and be able to score the video based off of that. And we found the correlation to how people perceive the video as very close. Trying to get there, and you can kind of see this where we have the 4 different engines where we're kind of looking, and we can see these fingerprints of noise in these in the data, and pull that information out. And you can see this is sort of how it correlates with how people view stuff. Center line is on one side is how people view it, and we view it. So we actually do about a 90. Let's say 90, about 92% is where we're at right now, which is pretty good. So the idea is reduce the amount of false positives and be able to look at video all the way through from when it originated through, looking for that kind of noise. And the nice thing about this is repeatable. So this is like noise. You can see where it's been scored, and it's a fairly high number. It's a MOS score of 4.3. You can take a look. This is what a 2.9 would look like. Did I skip one? And then this is MPEG at 3 to 1. You can kind of see a little bit of blockiness in there. And this is MPEG 2. It's at 2. So you're starting to see that polarization kind of effect going on there. This is what we want to be able to pick up. Now, if this occurred in the compression prior to the transmission, we might not have seen this in our standard way of doing things. But this picks that up. And that's just plain bad. Well, either that or the girl's looking at a lake. I'm not sure which it is. So anyway, but you can kind of get an idea of what we're trying to achieve here. And so here is noise. And also you see that little square? That's points of interest. Now this one is so noisy, we can't even see enough detail to figure out where the most detail is to put the point of interest in the right place. Because if you notice, most blocks have been around there because that's where most of the detail is. That's where people's eyes are going to go to. If there's noise up there in the upper right corner up there, people aren't going to notice that. And so we score that less if the noise is there than we do that point of interest. The other thing that happens, if it's a noise is there for a very short period of time, we don't score it as much because people don't notice that. But the longer it's there, the more it affects the score. So if the thing persists, we're going to take a look and we're going to score it downward for long periods of time. And because that momentary hit, one frame, most people don't see that. But a lot of us in the business do. I used to do QC at Crawford, and you got to the point where I could pick out the film noise and all the film videos, all the videos. It's that little thing pop up, and I'd see, oh, there's that. My wife, what are you talking about? Anyway, but so I eventually got over that. So but you can see here, we're looking for that highest grain where we're predicting where eyes are going to light. And that's what the highest scoring is going to be. So doing the measurement, you have something like this. And this is the measurement for how far down? A 43-minute clip. And the spikes up and down. That red line is at 2. And that's the line I said, if I have something below that, I care about it. I don't want anything to go below that 2. So I'm going to scare and give that result there. And so you see most of the stuff is up there. There's a few spikes down. The other thing that we've done is we've actually made a histogram of it. And you can see the stuff that's below 2%, very small numbers, the actual frames themselves. So it gives us a good way of looking at it. You can set the threshold wherever you want it to alarm. And what we're finding is it does a really good job of being able to detect what people what the idea is not to get people to change the channel, right? Because of technical problems. As engineers, we can't always control what people are watching or the content, but at least we don't want people changing the channels because of something we did. And so this is one of those things that we're looking at, is trying to get that down to that point. And if this is our Sentry product, we have a thing called reason codes. So we kind of invert the screen so you can see it. And if you look at the dark blue, that's tiling. So most of that error is caused by tiling. Then the blue at the very top, that's the noise. So we're taking a look and you can kind of see the different ways we can actually tell you what's causing it. We have a little MPEG 2, a little MPEG 3 going on this. So we actually can separate those out. But overall, the score is pretty good. Yes? Yeah, well, basically, with something like that, with the short depth of field, where it's sharpest is we're going to get the most score, because that's where the most detail is, the data is there. So the other stuff we probably score less. But it's one of those things we do. We give it over 2,000 different clips to look at. Now, this technology was originally developed in Texas University, Texas University. It was called BRISC. And you can look it up online. And their goal was to actually just look at images. And they were teaching it so you could pick out a Coke can from a Pepsi can, a bird from a cat, and basically find different images within a picture. And so we took that technology and put it into clips of video itself and taught it not what objects, instead of teaching it what a Coke can is, we taught it what noise looked like. And the nice thing about this is we've trained it for these 4 at the moment. It's one of those things like we can train it for other things. Right now we have a set pattern. We're not taking that much input from other people, but the idea is down the road, as we perfect this, we will be able to take input from clients and say, we have these troublesome sleeves. How can we add this to the overall intelligence of the system? Yes. Well, here again, we're looking for we're looking for geometric blockiness. We're looking for those kind of things. At some point, when it's just so much noise or so much random things, well, we do it with, we do what we can with it. But here again, if it's that much, if it's here again, when people look at that, it's really hard for people to take out special little noise in that anyway. So just like AI can't pick it out, if we can't pick it out, people really can't identify that stuff as well.
Technology is to help guide you to where a potential issue
Right.
is, not to fix an issue. Because
No.
again, if it's artistic like that,
Yeah.
shallow depth of field, or maybe somebody wanted it blocky, it's just going to tell you it's blocky, and then you're going to look at it and go, oh, that's artistic.
Yeah, and that's always been the problem through this. I remember sitting at Master Control once, and all of a sudden, I saw noise like we were off the air. I jumped out of my seat, and it was that darn commercial. I forget who made that. It would go to the noise and then come out, and that got me every time. It was back in the '80s, and it was just like it just got me up out of my chair every time, and I hated that creativity, shall we say? Huh? Yeah, I know. So anyway, so it's just one of those things you have to, art, artistic license. Here again, we are going to QC it. We're going to point out these points that are bad. The nice thing about this is it works both with our Aurora product, which is file-based QC, and also our streaming Sentry product, which looks at the streams individually. And we get the same score for both points. So you can actually say, all right, this file scored this. Now it went through this chain. Now the score is this. We know it's going to go down because we're going to molest the picture in some way or data in some way anyway. But how much does it go down? It also can help you determine that.
So, Turner, they've been using Sentry for years. Is that much going on? Is there a limit to how many channels then you can do?
Yeah, it depends on your box. I think we can do about 50. The other thing we can do to lighten the load, you can skip it where it checks every 6 frames or something like that as well, just so you can add more to it. But the idea, yes, it can be intense. The nice thing about it is it can do the analyzation in real time as it goes through that. But the whole idea is to be able to look at that and compare it and say, or give that area a score. So I think, yes. I don't remember. I have to look at it on the slide. I don't remember the numbers right now, but I believe I had to get that information for you. Sorry. Well, it basically is going to figure it out on its own. It's basically if we teach it wavelet, then it's going to look for those. Each of these errors have a certain pattern to it. So these are all running at the same time. These 4 are running at the same time. We're looking at the noise. We're looking for 4K, MPEG 2 and MPEG 4 and blurriness. We're running those all simultaneously and combining the scores at the end. Not really, because PVQ gives us a little different view of the image. It gives us a technical view of the image. The nice thing about PVQ is the score is high there and it's high here. That tells me it's from this stream itself, not something in the past. So it gives me a way of being able to help send it down. And PVQ is still going to be there. This is just a different way of looking at it. It gives us another perspective, shall we say, and more of a looking at it from our more artistic eye rather than a technical. PVQ is more of a technical measurement, and PVQ does score, I think, around 60% how people view it or something like that. It's just not quite where it needs to be. Was it about 60 or something?
The thing that I always remember was that you can take really high quality impressions that is almost completely flawless, and it's a 3rd generation extended play VHS. It still looks like it was played third generation VHS.
And so that's the difference. And so this would pick up that this is a poor quality video, where that would pass it because the structure of the encoding looks good.
I've seen some tools that if black or freeze is part of the picture, it lowers its loss score.
Mm-hmm.
How does this handle things like black? Let's say it's like that's considered a freeze.
We actually do that with a different scoring in our parks. So that's a different test measurement. That we don't add that into the formula of this per se. We'll tell you that black is blocky, or tell you if it's. But here at Peak, TechMoss is not going to do it. But we have other tools running in the same product that flag those things. So like I said, we can train the distortion, and we're looking at the classics. And here, this is, like I said, it's one of those things that we're just kind of breaking the surface of how this works and training this. And it's a tool we think is going to be revolutionary in how we look at video and be able to really, yes. That's more what the Brisk product does than what we're trying to do. Yes, technically we could. We technically could, but I don't think that's not our focus. We're, you know. Yes, actually, this would have detected that. It would have. Yeah. Well, the problem is that my understanding is it was blocky on the input side, so compression and stuff. So it would help detect that kind of issue. The nice thing about it, I think we'll be able to do in the future, is be able to help us determine whether this is good peak, whether it's good high dynamic range or not. I think that's something we could probably train it. We haven't done it yet, but I can see where that could be a way of helping look at that as well. Because a person can see the quality of high dynamic range when you see it. But yes.
Could also detect, like, for artifacts that cause, say, the lens was really dirty or something like that, or the really physical artifacts that was observed during a shot that maybe never missed, that might be able to detect those kind of abnormalities.
Well, we'd have to teach it those. Yeah. Well, the reality is we could probably teach it that, but here again, at some point in time, we should let the photo director actually pick out a few things himself, you know. I mean, here again, yes, we're looking at this more trying to look for the technical errors of the process, not so much as creative errors or human errors like that. But reality, yeah, we could probably. Are we going to? You pay us enough money, we will, you know, so.
So if I understand correctly, one of the values of this is that you're looking at it from a human perceptual perspective as well. We can have a scope that says this is bad,
Right.
but a human being may not see that as bad because of all the other stuff. So you're trying to, if I understand correctly, in essence, use AI to sort of weed out the true things that are technically wrong that create a bad picture versus the technical things that are wrong that a human being won't.
Right. There's technical things that we, as knowledge people in the business, will notice that our average person won't. And so our job here is to kind of score it a little bit towards the average guy. You know how people are going to look. Like I used to be for a long time. Every time the compression shows on and they do a dissolve in one place, there you get that blockiness. You know, now I'm just thinking in my mind it's an effect. You know, but I see it every time there's those dissolve. You see the little squares and blockiness that go on. See how much compression it is. I recently got a high dynamic range TV, and I've been watching a lot of shows with that. And I actually find one of the things that, and the nice thing about it was my wife noticed the difference. So the money I spent, I wasn't hearing about why did I spend money, because I can't see any difference. She could see the difference. So that tells you high dynamic range, actually you can tell the difference. And so by looking at it, one of the things you have to realize, high dynamic range, it's not really bright color when you do it right. It's things looking natural. It's just it's looking at the, you don't have the high the contrast is not sort of whacked out. It's sort of like when I used to go out and take photos. I'll do a lot of digital photographs and everything. Every time I took a picture, it didn't always look exactly the way I personally saw it. And high dynamic range gets you closer to that way you're actually there and you saw it, how it looked. And that's what I like about it, is that it's not overpowering in color and brightness like that. It's natural. And I used to run master color the news back in the 80s, and people would get mad at me because I tried to adjust the chroma so it looked as natural as possible. They want me to push the chroma, push it. You know, this is color. Everybody wants to see color. And so you know, but I really appreciate the fact that it really looks that. The other thing to kind of let you know, you notice it says Telestream up here now, is because we have been bought by Telestream. And that's just the video portion of Tektronix. Theoretically, I should be, you know, it was supposed to happen last week. During the holidays, they ran short of time, so they pushed it off a week. So probably this time next week, this will say Telestream. And, you know, but the products are the same, support's the same, we're moving on. We get, Tektronix is video portion, video division of Tektronix is only about 10% of it. So you got the oscilloscope people, the spectrum analyzer folks, and all those digital process, those all guys there. And since they're 90% and we're 10%, every year after NAB, we had to make a case to be able to go back to NAB because the rest of the company didn't know why we needed to do that. Those are part of the video. So that's the stuff I support, and I am going to, and all the engineers who design that, all the people who design Sentry, all that products, everything under that emblem that the sales guys you work with, everything we sell is going to be part of Telestream. And so, you know, I will support that. My phone number doesn't change. My email is not going to change for a while. So, well, unless my wife kicks me out for not cleaning it. That's, yeah, I think we're going to call it that. We have right to use Tektronix for about 3 years. So something like that. Our ownership, the Fortive, who owns Tektronix, is own 30% of Telestream. So it makes things a lot easier. So it's more of a merger than a buyout, total buyout. So, but anyway, it just gives us a more video-centric group of people to work with.
Do you happen to know what other companies are using that approach?
I don't know. You can look it up, and they actually have a nice little GUI on there and show you how it works and stuff. It's kind of a cool website to go look at. But they started it, and we took it and redeveloped it to do something a little, you know, get away from stills and do video itself. And so, you know, and it's kind of an interesting thing that they're doing with it. And I don't know if we're going to change the name of it from TechMoss to Telmoss. I don't know. So anyway, but that's pretty much it. But anyway, pretty much what I have today. Any other questions? I'm really excited about this technology. This is really cool stuff. It's one of those things that kind of, that slide you saw where I had the thing go across and you saw the colors change differently. I was using that slide 2 years ago to tell you not to trust your eyes because the waveform could tell you that that's wrong and your eyes didn't. But actually, as I was telling people that, I'm saying, well, you know what? We're actually doing video for people. And that's where we had to, that's where this helps us with that. We finally have a tool that looks at video the way people do. And so anyway, so that's I think is what really is the value of it. And it doesn't surpass the other tools that we have. It just enhances what we have, because you still want to know the technical strength of the signal. Just because people didn't notice it on this particular signal, they may notice it on the next one because how it wraps right. So we don't want to necessarily get rid of looking at the structure of the video, but we also want to look at the quality and how it's presented as well. There you go.